The next scheduling algorithm that we are going to see is shortest job first algorithm. So as the name suggests, the shortest job, that is the shortest job in the sense the job which is having the shortest burst time, shortest next burst time, it will be getting the hold of the CPU. So that is why it is called as shortest job first. The other name is known as shortest job next. It can also be abbreviated as SJN or SJF. So this algorithm, it can be either non-preemptive or preemptive in nature. Done. Let's see this with an example. So these are the process IDs, and this is the arrival time of each process, and these are the burst time of each and every process. And now we are going to discuss about the shortest job first, which is a non-preemptive case. That is non-preemptive in the sense, once a process is getting the hold of the CPU, it will not be taken out of the processor until it completes its execution. So in SJF, we can have both non-preemptive case and also the preemptive case. And in this non-preemptive case, we are going to see with different arrival times how this shortest job is getting the hold of the CPU, and how the arrival time is affecting the job's entry into the CPU, and how it is the waiting time and the completion time it is varying with respect to FCFS, right? So in non-preemptive case, just by seeing this given table, we can find that the first process which has arrived is P1, because it has arrived at time 0.0 itself. So even though the burst time of P1 is very longer when compared to all the other three processes, it is not shorter, right? It is very longer. But even though, since it has come first, we have to allocate P1 to the processor before allocating these three, because these three processes have arrived only by time 2, 4 and 5 respectively. But the first process to arrive to the ready queue and it is ready for execution is only P1. So even though the burst time is smaller, you may get a question that since it is shortest job first, we need to pick only P3, but P3's arrival time is only 4, because at 0th time it has not even arrived, so we can't choose this process, right? So we need to choose P1 process to get its execution. So P1 has arrived at time 0, and it has to be given to the CPU. So we have given P1 to the CPU, and it is getting its execution till 7, because its burst time is 7. And why we are allowing that to get executed till 7? Just because it is non-preemptive. Because in non-preemptive case, once the process is allocated to the CPU, we cannot take it out. So from 0 to 7, P1 will be executed. Okay, now 7 milliseconds has been completed, right? From this we can see that P1 was holding the CPU for about 7 milliseconds, and during this course of time, all the processes which we have listed here, because P2 has arrived at time 2, P3 has arrived at time 4, and P4 has arrived at time 5. All these processes would have entered into the ready queue before this P1 completes its execution. As we have know how this ready queue allocates each and every process as it arrives, it will be present in the ready queue, right? So this arrival time denotes that all the three processes P2, P3 and P4, they would have come inside the ready queue for its execution and waiting till P1's completion. And once they have all arrived in the ready queue, our selection at the next turn, it will be with respect to the burst time. So these three processes have arrived by time 7 millisecond, and now we have to choose the most shorter process among these three processes. So as we can see, P3 process is having 1 millisecond execution time. So this is very less when compared to both P2 and P4. So that we are picking P3 as in the next turn. So in the 7th millisecond, P3 is given to the processor and it is executing for 1 millisecond. So from 7 to 8, P3 will be executing and it will be getting the hold of the CPU, right? So after that, there is a tie between P2 and P4, because both the processes has arrived at time 4. Both are having the burst time as 4. So both are having a tie. So we need to dissolve this tie and give a single process to the CPU. So in order to resolve this tie between these two processes, we need to then look into the first process which has arrived. Now the algorithm, it works like FCFS, that is first come first serve. So among these two, which process between these two, which process has arrived first? So the arrival time, it tells us which process has arrived first. So 2.0 P2 has arrived first. So we are giving the CPU the hold of the process P2. So we are giving P2 to the processor. So P2 is executing 4 units of time from 8. So up to 12 it will be executing. And then we are giving the last process P4 to the CPU, and it is also having 4 units of time, and it will be executing from 12 to 16. So totally we can see the Gantt chart, and we can see the total execution time is 16 for this given problem, right? So the average waiting time of P1, it will be 0. So the completion time is of P1 is 7 and the waiting time is 0, and the completion time of P3 is 8 and waiting time is 7, and the completion time of P2, it is 12, and the completion time of P4 is 16. And from these completion times, by subtracting the completion times with the arrival time, we can find out the turnaround time of each process, and the turnaround time minus the burst time, it will be giving you the waiting time. The average waiting time can be calculated by consolidating and dividing it by 4. Here they have directly given you the average waiting time. Actually it can be computed by computing the turnaround time first, and then from turnaround time, if you subtract the burst time, you can get the waiting time of each and every individual process, and by getting a average of all the 4 processes, you can get the average waiting time for this process. So average waiting time in this non-preemptive case is 4. Okay, so now we can see the same example with preemptive case, under the preemptive case. So the preemption in shortest job first, it can also be, that algorithm can also be called as shortest remaining time next, right? Because we are going to look into the execution time which is the shortest time of the next process which is arriving to the CPU. That is why it is called as shortest remaining time next. So now the processes and the arrival time, their burst times are given here, right? So now as we know, and this is a preemption case. So preemption case, what is preemptive? If we are getting any other higher priority processes, higher numbered processes, which is it may be in any case. If it is a higher priority process, we have to give the CPU to that process, and the currently running process, it should be taken out of the CPU. That is what is known as preemption. Okay, so now we are going to see the same problem under preemption case. So as we know, the arrival time is 0, so definitely the process P1 should be given to the processor. Okay, so we have allocated processor the process P1 to the processor. So it starts with 0 and it is starting its execution. So you imagine that at time 0, only the ready queue will have only one process, which is P1, right? So it is taking the process and giving, the scheduler is picking the process P1 from the ready queue and giving to the CPU, and CPU is processing. And now at time P2, that is at time 2, P2 has arrived, and P2 is having an execution time, burst time of 4, right? So now P1 at time 2, it would have executed 2 units of burst time, right? So 7, it will be, it would have become 5. 7 minus 2, which is 5. So at the second millisecond, P1 process will have the remaining burst time of 5 milliseconds. So now you compare the newly incoming process, which is P2 at time 2's burst time, and the remaining burst time of the previous process. The remaining burst time of the previous process is 5, and the newly incoming process burst time is 4. So which one is shorter? P2 is shorter. So now we remove P1 from the CPU and give the CPU the hold of process P2. So P2 is given to the processor at time 2. Since because 4 is shorter than 5, we take P1 out and give P2 to the processor, and P2 will be executing from time 2, right? So now it will be executing till the 4th millisecond, because at time 4, because during the 3rd millisecond no other process has arrived, and at time 4 we we encounter P3 process. P3 process is having a burst time of 1. At time 4 it has started from 2. So at time 4 what will be the burst time of P2? Definitely 2 milliseconds would have been completed. So the remaining will be 2. But you compare 2 with 1, which one is shorter? P3 is having the shortest burst time. So P3 will be given at time 4 to the CPU. So at time 4 we give P3 to the CPU. Since 1 is shorter than 2, remaining 2, we give P3 at time 4 to the CPU. So P3 is given to the CPU, and it is burst time, its burst time is only 1 millisecond. So from 4 to 5 it will be executing, and at time 4 it will complete its execution totally. Now it has started from 4 and it has ended up to 5, and at time 5 already a process burst time of 4 it has arrived. Now already we are having P1 in the ready queue as 5 with 5 milliseconds, and P2 with 2 milliseconds, and P4 with 4 milliseconds. So among these three processes, now all the process has arrived into the ready queue. Now among these three processes we need to choose the shortest job. So now this algorithm, that is after all the processes has arrived into the ready queue, this shortest remaining time next algorithm, it works as if a non-preemptive SJF algorithm. Now we need to choose the shortest job, that is the shortest process which is having the shortest burst time among all the processes present in the ready queue. So when we compare and see, P2 is having a remaining shortest burst time of 2 milliseconds. So P2 will be given the hold of the CPU at time 5. So it will be executing for 2 milliseconds. So the completion happens at time 7, right? And after 7, now compare. P1 is having a remaining burst time of 5, and P4 is having a remaining burst time of 4, a shortest burst time of 4. So P4 will be getting the hold of the CPU next. So at the 7th millisecond, P4 will enter into the CPU and it will be executing till 4 seconds. So from 7 to 11, P4 will hold its execution, and at the 11th second, this 5 burst time, the burst time of P1 process is having a remaining burst time of 5, right? So the 5th, that is a P1 process, will be given to the CPU and it will be executing till 60. So when you see these two, both the processes, both the Gantt charts are telling us that the overall execution time is getting over by 16. But you can see the difference in the waiting times of each and every process. So now if you compare and see the completion time of each process, P1 has completed not at 2 but it has completed at 16th millisecond, right? And P2 has completed not at 4, it has completed at 7th millisecond, and P3 has completed at 5th millisecond, and P4 has completed at 11th millisecond. So while calculating the turnaround time, you need to find out the, for example, the turnaround time of P1, if you take 16 is the completion time minus 0 will give you the turnaround time of 16 for P1, and for turnaround time of P2, 7 minus 2, that is 5 will be the turnaround time for P2, and for P3 the completion time is 5, so 5 minus 4, 1 will be the turnaround time for P3, and for P4 it is 11, so we need to subtract 11 minus 5, and the turnaround time will be remaining 6. So likewise, from the turnaround time, calculated turnaround time, you need to calculate the turnaround time minus the burst time. It will be giving you the waiting time of each process. Likewise, we have calculated each and every waiting time of each and every process, and the average will be found out as it can be divided by 4, that is the total number of process. We can get the total average waiting time. Now if you compare the average waiting time of the non-preemptive case and the preemptive case, we can see a difference of 1 millisecond. So this shows that the waiting time is reduced when compared to non-preemptive case, and also when compared to all the rest of the other algorithms, scheduling algorithms, the most shorter waiting time and the turnaround time can be found only in case of SJF, or that is shortest remaining time next, that is a preemption case of SJF in scheduling algorithms. So this is the most the best algorithm among all the other scheduling algorithms. So with the remaining two algorithms we can discuss in the next class. Thank you.